record. Okay. So we got the recording going. Let's see, this is the train PowerPoint on the economics of gas cooling. And I think we're on slide 13. We'll hopefully finish this today. And let me see here. View and yeah, that's what well, let me see. View. This is what we've been doing. Okay. I kind of like this because we can we've got the notes right there, and in some cases these notes are pretty good. Sometimes they're not, but sometimes they're worth looking at. Let's see. I think we may have done this at the end of class before this slide, but basically we just looked at the operating cost to produce a ton hour of refrigeration. And remember, a ton is 12,000 BTUs an hour, so a ton hour is 12,000 BTUs of cooling per se. You know, we're going to use a gas rate, 45 cents a therm. And again, a therm is 100,000 BTUs. So 10 therms in a million. And so that's $4.50 a million gas, which is the way we usually talk about gas cost. Centrifugal has 0.6 kW per ton. Let's see, I don't know if we calculated that before. And I think that came out, what, 5.85 on the COP from last class. So, you know, the comment here is if we're just moving BTUs from electricity to gas, it may not be such a good idea, you know, just given this cost per ton hour. So what we're going to do now is we're going to develop, this is the goal, I don't know, probably some engineer at this first assignment, but it's to design an application that uses a direct fired absorption to reduce as much demand as economically possible. And so this is going to look at a particular rate structure where we've got on peak, off peak, where on peak energy, which is when in the summertime the cooling load would be the highest, which is when the chillers would be operating, and the chiller is probably the largest electrical load in the building. And so we're going to see if we can come up with a scenario that makes these absorption chillers look financially attractive. And so, and this is a real situation that occurs. Okay. So in the economic analysis, you know, it's funny, we all, you know, in engineering, we like to do BTUs or, you know, energy flows or stresses or strains or PSI, you know, whatever. But out there in the world, it's the dollars. Everything eventually gets translated back into dollars, and that's where the decisions are made. So being good at doing the cost analysis, the economic analysis, that's a huge skill. So all the things that are going to be included in this are, you know, the first equipment cost. You know, when you do the economic analysis, how much does it cost to buy one type of chiller versus another? And absorption are a little more expensive. Install cost, is there a difference? Operating cost, maintenance cost, total system cost, and then specific load profiles that might, if we can conjure up the right one, we might be able to make this absorption look economically attractive. Okay, so he's got, I think, at least three slides here looking at different ways that they call them hybrid chiller plants. And by hybrid plant, I'm getting notices popping up on my computer here. A hybrid plant will have a centrifugal and I say an absorption, and there are other types of chillers that I guess could be involved in a hybrid plant. But for this example, we're going to be looking at the centrifugal, big centrifugal electric, and then the direct fired absorption. So so we'll have a couple of different piping diagrams here and then some comments about it. Okay. So it says, we'll evaluate some hybrid plants, different ways you can put them together, positives and negatives. A common arrangement is a parallel decoupled system like this, which I guess is pretty simple, but it has some drawbacks for us. So this system, once you get above 100% load on either chiller, then it's going to equally load the chillers. And so we'll read this note down here. It's pretty good. The drawback of this type of system is what we're trying to accomplish is that the units cannot be preferentially loaded. Once one of the units is loaded above 100%, the second unit turns on and both are loaded to 50%. So you'll be able to reduce your demand, but not as much as if we use an alternative system because of the way we pipe it and the way you have to operate these chillers when they're piped like this. It limits our ability to reduce the demand as much as would be possible with other piping arrangements. Okay, so that's the first one. And then the second one, and there's a couple of interesting notes here, but in series, and notice this it says used with high delta T systems. Notice we got 58-degree water coming back from our building or from our system going out at 42. Well, 42 is pretty standard, but what is it? That's a 16-degree delta T. That's a high delta T system. Now, that really brings up several interesting issues. More recent design concepts are starting to favor higher delta T systems because, the higher the delta T, the lower the flow rate and the smaller the pumps, the distribution energy, and the amount of fluid that you have to flow in order to distribute this cooling capacity to your building. If you've got a 10-degree delta T, you're going to have more water than if you got a 16-degree delta T. Now, older chillers and stuff didn't necessarily like some of these different flow rates, but they're becoming much more flexible. So the very newest designs sometimes will reduce condenser water flows below what they traditionally have been, and we'll talk more about that, especially when we get to cooling towers, and also increasing the delta T on the chill water side so we can reduce the flow rate. So kind of interesting. So in this scenario, we can load either chiller we want to. Takes advantage of high temperature capabilities of the absorber, low temperature capabilities of the centrifugal. And so we've got another note down here. They'll talk more about that. The issue right now is that we're pushing all of the water through both chillers. Well, that's fine if we're using both chillers, but what if we're just using the absorber? Well, we don't want to pay for the pressure drop across the evaporator in terms of the chill water flow. And so as drawn, that would be a detriment. Now, we can put bypasses around these things, which is probably what the designer would want to do if they didn't turn out to be too expensive. You would have to evaluate that versus the extra pumping energy. But for example, if you're using the absorber, when you come out at 50 or whatever degrees, if you're done cooling the water, then you could have automatic valves where you shut off the flow here and you simply bypass around the chiller and you don't incur this. It's probably 15 to 20 to 25 feet of head loss across this evaporator coil. And there would be not very much at all. There would be some through the extra piping and valves, but maybe 4 or 5 feet, something like that. So there would be a large reduction in the pressure loss that you would see as compared to if you piped it up like this. Okay, so let's see the notes. So this arrangement solves some problems. We can load either chiller and take advantage of your electrical rate structure. This last kind of interesting. or next to last note, I guess. Using the absorber upstream enables you to use the absorber for the higher water temperatures. So say we're showing 58 degrees, which is pretty warm. Um, so for example, if we had an absorber that produced 500 tons of cooling at ARI, that's oh golly, I'm blanking out. Refrigeration Institute, is American ARI. It's they establish rating conditions for chillers. I'll think of it in a minute. But so the standard that this would 500 tons would be rated at is probably a 12-degree delta T, say. Conditions, and now put by raising, well, it says raising the leaving water temperature, but we're by putting in warmer water to it. So I guess he's really talking in terms of leaving water temperature. This thing at 50, which means we went in at 58, we have a 600-ton chiller, which could be interesting. Now, in the dead of summer, you're still going to need 42-degree water, but in the spring, the fall, and even the winter, when you have a large building that still needs air conditioning, it may be able to get by with 50-degree water just fine, because it's really dehumidification that's the issue on having the cold water. So it's an interesting concept. So, and then it just says the system is sensitive to pressure drops, and we already talked. Freeze flow. Right. Stream arrangement. So what you do is here's your return water coming back. And so you're much more flexible. So if we want to put the warmest water into the absorber, we can do that, make it as cold as the absorber can make it. And then if that's cold enough, we can then go through the bypass line and go right back out to our system. If that's not cold enough, then we can take that water that's been cooled partially and run it through either one of these centrifugal machines and make it as cold as we need to make it. So it's certainly more flexible. So this is the one that they're going to use in the evaluation here. So that's called the side stream arrangement. Okay. So here's the electrical rate structure for DC. And notice on the energy charge, they have actually 3 periods a day. That's kind of interesting. So they have on peak, mid peak, and off peak. They tell us what the on peak is because that's really the one that they wind up, well, we actually calculate a cost for the chillers for all of these. But apparently there's only 2 demand peaks, I guess. I don't know, maybe there's 3 demand peaks, but they don't tell us. So this is all we have on the rate structure. But notice the on-peak demand charge is $12.55. The off-peak is probably half of that. And then we have the maximum demand charge of $10.25. So basically, if you set your peak during the on-peak period, each kW is going to cost you $12.55 plus $10.25. And so that's what's really driving this analysis. Okay, is there anything else here? And, they just make a comment that, in the summertime, with a centrifugal chiller, some information on looking at the operating cost for a typical office building. I can make that a little bit bigger. And demand charge. you'd about a 50-50 split. 50% of your electrical bill comes from the actual energy that you consume, and the other 50% comes from your demand charge based on your peak rate of using power. But if you look at just the chiller plant itself, analysis will show that typically the demand charge is about 61% of the total, and energy charge is only 39%. And that's because that's typically a centrifugal chiller, and they've got big motors in them, and that really affects your demand charge. And they will operate heavily loaded just during a portion of the day, and then they back off during the rest. So during the rest of the day, the energy falls, but you've already set your demand peak. So you're going to get damage back. Okay, so let's look at, they're going to calculate the operating cost. And let's see, so this is for the direct fired chiller. Okay, and so what we want to get is we want to get dollars per ton hour of refrigeration. And remember, a ton hour refrigeration is 12,000 BTUs of refrigeration. And so if you look in this top bracket term, there's your 12,000 BTUs per ton hour. So that's the refrigeration. Well, the input energy we can get by dividing by the COP. Coefficient of performance is what desired output divided by costly input. And so this is output and this is output over input. So when we divide, the outputs cancel and we get the costly input in terms of BTUs. And then how are we buying this energy? Well, we're basing it on 45 cents a therm. So we have to convert those BTUs to therms, and that conversion is divided by 100,000. Okay. So this is going to get me therms per ton hour refrigeration, and then I multiply it by the cost, dollars per therm, and I get dollars per ton hour. And so he's using, for the direct fire, the COP was 1.03. It says that in the notes right now below. So you take 12,000, divide by that 1.03, and then divide by 100,000, and I guess you get 0.1165 therms per ton hour, and then times the rate of 45 cents per therm, and there we go. So it's this is dollars, so that's 5.24 cents per ton hour for the direct fired to provide the refrigeration. There is a very small electrical load associated with that he's not including. So and I think we just went through that. You can, it wouldn't be a bad idea. Just run through the math just to verify. Okay. Yeah. Cost for centrifugal. And so here we have demand and energy. So it's kind of interesting to see what he does on the demand. So it's kind of like the COP on the machine. It's not really a COP because it's got units, but it's the efficiency of the unit, I guess you'd say. So it requires 0.6 kW of power per ton of refrigeration. And notice that's a rate over a rate, because kW is what? Kilonewton meters per second, and ton is BTUs per hour. You know, we've got all kinds of units floating around, but it's a rate over a rate. Okay, so if it's 0.6 kW per ton, and we're charged demand charges per kW, so the charge is $22.80 for that on-peak period when it's the max demand. So it's $22.80 times 0.6, so we get $13.60 per ton. And now, okay, he's gonna spread this out over this 184 hours. So you need to. So we determine the number of run hours. So this is the number of run hours in the month. This is basically in a typical month. Okay. So what he's doing, he's multiplying the number of peak hours per day on like a weekday, which is, he's saying is 12, from 12 to 8. So that's 8 hours of on-peak time. And there are 23 weekdays in a typical month on average. So if you multiply 8 times 23, you get 184 hours. And then we're going to spread this demand charge out over all of those hours. So we can add it to the energy charge, which we have to get all this on an hourly basis. Okay. And so they say, okay, this is what the energy, the demand charge would be, $1360 per ton, but we're going to spread that over the 184 hours that this thing operates. So we get about 7.39 cents per ton hour on the demand cost. And then the energy is a little more straightforward. It's just 0.6 kW per ton. And so if you ran that for 1 hour or for 1 ton hour, then you would get, so you're assuming 1 hour in here. And so 0.6 times the rate, 5.32 cents gets us another 3.19 cents per ton hour. And so the total cost of operating this is demand plus energy. Add them together, you get 10.58 cents per ton hour. Okay. So then through and said, okay, well, for the direct fire, it's the same cost because its rate, that gas rate, we're assuming doesn't change. So it's the same 5.24 cents per ton hour for on-peak, off-peak, mid-peak, whatever. It's the same throughout the year. Centrifugal, though, changes because the electric rates change. Okay, so if we run it off-peak, then that demand charge is much less. Okay, so we see off-peak centrifugal 1.64. Wow, that's really cheap. That's much cheaper than the direct fire absorber. Mid-peak 2.47, but on peak there's the 10.58, and then the winter on peak is 5.88 cents per ton hour. So now we kind of get to see where we can generate some savings because we have a big cost advantage for the absorber compared to the centrifugal for the on-peak summer hours. It's roughly, so it's not quite, but well, 20, not quite, but it's pretty close to twice as much to run. In fact, it's a little more than twice as much, isn't it? Yeah, it'd be 1048 versus 1058. Okay. All right, so now here's our example building. It's in Washington, D.C. We've got 1,000 tons of load. We're going to have 2 chillers in the building. We're going to have a 400-ton direct fired absorber, a COP of 1.01, and a 600-ton centrifugal electric that's 0.6 kW per ton. Design conditions are leaving chill water temperature of 42 and entering condenser water or cooling tower temperature of 85, 45 cents a therm for gas, and it's the Washington, D.C. rate structure that we've already looked at. Okay, let me make this just a little bit bigger. Well, let's see, but let's read this here, make sure I get it right. The blue area represents, the operation of the direct fired absorber. Okay, so. Okay, so load profile for a typical summer day. So it's probably a design day or something like that. And so you see that over here in the heat of the day, 1 p.m. or 2 p.m., 3 p.m., something like that, we're probably 950 tons, something like that. We got 1,000 tons of capacity. Looks like they did a pretty good job sizing the chillers. If this is a design day, got them just a little bit bigger than we need. And so you see in these off-peak hours, we're going to run the centrifugal because it's cheaper, okay? So centrifugal, 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 and all of a sudden now, in this hour at 8 a.m., we jump up and we've got an 800-ton load. So guess what? We can't do all that with a 600-ton electric, so we got to run both of them. So then the absorber gets fired up, and it's brought up. But see, it's kind of minimal. We're loading. This is 600 tons. We're going to load this centrifugal to the max because it's still cheaper until we get to the on peak. So on peak starts at 12 o'clock. So right here. So at 12 o'clock, we load the absorber to its max, and then the centrifugal basically trims the system, provides the required additional cooling, okay? And so we're going to max out that absorber for all of these on-peak hours, which starts at 12 and runs all the way over here to 8. Well, say when we get past, there's 4. When we get to 5, well, we can do it. Well, looks like that centrifugal may just be slightly operating. I'm not sure. It may be off. Maybe it's off. Looks like it's off, I guess. But anyway, so during this on-peak period, you're going to bring this centrifugal down as quickly as possible. And so once the load is 400 or less, we're just going to operate the absorber until we get to the end of the peak period, and then we're going to shut it down and go back to the centrifugal because it's cheaper. So, I mean, we're just doing our best. And, you know, if you had this operating, you probably would want it to happen automatically, where you had automatic controls that were programmed. So it, you know, based on time of day, the system knew, okay, we want to max out the centrifugal over here. And then all of a sudden, you know, right here, now we want to max out the absorber and trim, and all that sort of thing happens automatically. So that's pretty cool. The direct fire system saves approximately $27,000 per year in operating cost. So lower cooling tower flows can decrease installed cost while improving system efficiency. Okay, so there's a lot in that bullet point. It's not really obvious because, you know, for our standard absorber, it's going to require more cooling tower flow. But then later on in the slides, they're talking about some of the new train absorbers don't need as much condenser water as the industry standard. And so the train absorbers can reduce cooling tower flows. But if you're just comparing centrifugal to absorbers, even the train absorber, you have to provide more cooling tower flow for the given capacity chillers. So that middle bullet, I think, is a little misleading. Maintenance costs with new direct fired absorption or is low, and in some cases lower than centrifugal. That's one of, we'll have some slides here in a minute. That's one of the wraps that absorption chillers have had over the years, is that they require a lot of maintenance. They did this analysis in the Train Trace program, which is very similar to the carrier hourly analysis program that you guys are operating for homework. So it does about the same thing. Okay, so that's the end of that economic analysis. Now for the rest, I guess we've got about 15, 20 minutes left. So we'll see if we can get through these. We're about to finish the absorption stuff, and we're going to move on to cooling towers next. So I'll be sending you some more files, the presentation files on the cooling towers here, probably later on today. Okay, so technological advances. Let's see what we're talking about here. But history of absorption products, and you know, you can read this. I'm not going to talk through processor controls. That's kind of a big deal in the 90s. You know, controls are much more sophisticated. Okay, historical problems. We've been through this. Crystallization, low cooling tower temps, power loss, air in the machine. We went through some of that. Slow response time. The old absorbers had difficulty in meeting changes in load. So, a big cloud, the front would blow through and the cooling load would go down, and they just didn't react very quickly. And then difficult to operate and maintain the machine, air, perking, service personnel, corrosion issues. To these problems, what have they done in, say, the last 10 years to improve all this? Well, better controls, upgraded materials, other features, and robust design. Combination of these things is how they have improved. Robust design, they mean that they have developed an absorber that can handle diverse conditions, can handle load changes. Unit controls are at the center of this capability. Microelectronic controls have the ability to closely monitor the cycle and make quick variation. So it just has taken time for all this to become more robust. Okay, so here we go. Now that you guys are experts on VFDs, you just have to be somewhat familiar with VFDs. And I may even dig up some more. There's issues with harmonics and electrical line links and stuff like that. I'll probably give you some more VFDs, because when you go out there and work in the world these days, these VFDs are everywhere, and you need to know quite a bit about them. But they put VFDs on their pumps. Part load efficiency is better. Response time is very quick, and it has allowed lower part load operation, which we'll get into on some of these notes down. Part load, turn down is now similar. By turn down, it's of your rated capacity, what's the lowest percent that you can still operate the machine? For example, if you had a 1,000-ton chiller, can you operate it at 200 tons? Can you operate it at 150 tons? So the older equipment did not turn down very well, which was a problem, which then you would have to cycle things on and off. And of course, turning things on and turning things off all the time is a lot of wear and tear on the equipment. So having higher turn down is a very big benefit to the equipment owner and operator. Talk about the burners a little bit and the problem shutdown capability. Okay, let's there. Some of this is pretty good. So they talk about the thermal flywheel effect within the absorption cycle. And that's like once you release that energy in the generator, it takes a while for the effect of that to be kind of work its way through the cycle. So once you put it in, especially in the old days, you were still going to get the refrigeration out, whether you needed it or not. If conditions had changed, so you might be producing refrigeration that you don't need just because the machine doesn't respond very quickly. So some of the things that they've done to give better response times is providing variable frequency drives on solution pumps. VFDs have the capability of short-circuiting this thermal flywheel to provide almost instantaneous response to changing load. And of course, the other benefit is it reduces the pump part load energy. So the efficiency is improved. Now able to run part load down to around 12% on steam and direct fired machines. That's pretty good turn down. Getting down to 12%, that's pretty good. They make a point to say here that, well, we save on maintenance of burners because we're not cycling on and off as much as we used to. And all other manufacturers, I don't know if this is true currently, can only modulate down to 30%. So you have to realize these are trained. We also solve problem crystallization on power shutdowns by using combination of normally open valves on the unit. Upon a power loss, the unit will go into gravity-fed dilution cycle that prevents crystallization. So that's pretty good. And as restored, unit will automatically restart and begin about improvements. Lower chilled water temperatures controls make it possible to go down to 40 degrees, which is colder than the older units could go. Ideal for IAQ is indoor air quality and retrofit applications. Hot water capabilities, we talked about that. We can get this auxiliary heating bundle. Ability to control for heating, preference, or cooling, and changeover can be done remotely. So you can change from a hot water priority to a chill water priority. It's very easy with the absorption. Past 42 was about the limit, and now we're down to 40. And so for indoor air quality, they don't really explain that. The only thing that I can come up with is that, for example, for humidity control, sometimes we have to cool the air pretty cold to wring enough moisture out, and then we might reheat it. I think we mentioned that before. And so if you got 42-degree chill water, you can wring more moisture out of the air, so you get better humidity control than if you only had 42-degree water. So that's what I can come up with on the indoor air quality. Direct fire absorber has the capacity to make up to 180-degree hot water, which of course we can use for heating or space heating or whatever. And the changeover from heating cooling requires no valving. It can even be done remotely. So that's a nice feature. Generator has to do with materials. So the most critical component, it sees the most aggressive service because it's got the strong solution of lithium bromide at the highest temperature. So that's going to be the most corrosive environment. And so by going to stainless steel, they can create a generator that will last 20 to 30 years, which is probably lifetime of the machine. So that's pretty good. And then some of the other areas, we can go to the copper nickel tubes, provide cost-effective solution for maintenance. So that's all corrosion. Okay, so other features, low NOx burners. Okay, so when you burn natural gas, you're going to produce some NOx. Now, there are different burner technologies that are designed, low NOx burners, obviously designed to reduce the amount of NOx. Depends on where you're putting these gases up. If you're in a non-attainment area where NOx levels are high, you have to be really careful how much they will limit the amount of NOx that you can put up from a given piece of equipment. You have to get a permit for it, and the permit will list the NOx, and you have to perform periodic testing. Power plants have to do continuous testing. They call it SEMS, continuous emission monitoring systems. Smaller things like a chiller, you probably are going to have an emission measuring company come in once or twice a year and just take spot measurements to guarantee that you're not exceeding your permit emission levels. How do some of these burners work? Well, one of the main mechanisms that NOx is created is by higher and higher temperatures. The higher the temperature in that combustion zone, the more N2 molecules that are in the combustion air will disassociate into an N and an N. And then there's also O2 in there at high temperature. It'll disassociate. And if the oxygen doesn't get used in the combustion, it's available to, combine up with an N that has split apart. And so you can get an NO, or you can get an N and an O2. In O2, those are the two primary components of NOx. There's also N2O. These things go up the stack, and then there's even further chemistry goes on in the atmosphere. But NOx levels are of interest, especially these days and going forward. So that would be something to consider. And burner technologies are getting better. Modularity, retrofit market. You can find units of size and they can be taken apart into a couple of pieces and shipped and put back together and all that. So lifting limitations. And automatic purge to get the air out of the system. We mentioned that before. More and more areas of the country requiring low NOx burner, and the train unit provides a standard. Also has an 8-to-1 turn down, which we mentioned before. We're going to valley here. Okay. Okay, so this is now this is where they actually provided some test data where they have done some various testing on their units. So this one, between 27 and 47 minutes, they're going to inject 6,000 milliliters or 6 liters of nitrogen and to simulate a leak, an air leak into the machine. So see, there's 50 minutes. So right in here, you can see where they start putting in this nitrogen. I'll blow that up a little bit so you can see a little bit. Control system is here. So up here on the top, we have the burner firing rate. And then we have the capacity on the machine. We have the evaporator entering, so entering water, EWT's entering water temperature, that's coming back from the system, and the actual leaving chill water temperature, and then the yellow is the set point. So it looks like the set point's down here, I don't know, was that 44? Looks like it's probably about 44. And so we're rocking along, we're right about on set point. We put all the air in the machine, and so what happens? That affects capacity. Capacity starts dropping. Now with the old controls, what would have happened is the controls would have sensed capacity dropping and it would have fired harder, which would have pushed us into a crystallization problem. But so they're bragging here about their controls. Look, the firing rate actually went down as the capacity went down because the controls realized that we have a leak. Okay, and so they don't want to crystallize, so they back off on the firing rate. Now we do get a bump in leaving chill water temperature. So, what is that? If that's 44, like maybe 46, something like that, 45 and a half, 46. So maybe 1.5 degrees, 2 degrees on chill water, which is not huge. And say, you don't see much of a change in the returning water temperature. So that would say it probably didn't really affect anything too much. But so you see over a course of a couple of hours, then the purge cycle works and we get the capacity comes back up and the burner firing rate is stayed stable through that whole period. So we didn't crystallize, and then gradually we start increasing once we get the machine back in proper operating condition. It firing rate goes up, capacity goes up, and we pull the leaving chill water temperature right down to the set point. Pretty interesting. So they talk before. I thought I'd get through all this today, but I guess I'm too long-winded. So I'll stop here. I'll be sending you some more files and perhaps another link to a YouTube video if I can find one on cooling towers. And let's see, chat, is there anything here on chat? There we go. Okay, that was just the password. Okay, so I'm going to stop the recording now and get off here. And let's see, this is Thursday, so I guess we'll be back together on Tuesday. I will be in the classroom for anybody that wants to come. And I'll be looking at your homeworks here. I think I have received most of them. If not, get them in just as soon as you can. I appreciate it. So be back in touch.